Imagine you drop a ball and without fail it falls to the ground. But what if I told you that at the same moment, the ground is also pulling up toward the ball? An almost imperceptible motion because Earth's mass is so enormous. It happens so naturally that we rarely stop to ask why. What invisible force pulls everything back to Earth's surface? More astonishingly, did you know that without gravity, the moon would drift away and our planet would spiral off into the void of space? This force, the same one that keeps the moon circling our planet and holds the planets in orbit around the sun, is called gravity. Gravity is a fundamental force of nature, yet it's also one of the most mysterious. At its core, gravity is the attraction between objects with mass. Everything with mass, from the tiniest grain of sand to the largest star, pulls on everything else. The strength of this pull depends on two things: the masses of the objects and the distance between them. The more massive an object, the stronger its gravitational pull. The closer two objects are to each other, the stronger the force between them. Isaac Newton was the first to describe gravity scientifically, laying the foundation for modern physics by providing a mathematical framework that explained planetary motion and the forces governing the universe in the 17th century. Legend has it that he began thinking about it when he saw an apple fall from a tree. Newton realized that the same force pulling the apple to the ground must also be what keeps the moon in its orbit around Earth. He formulated the law of universal gravitation, stating that every object in the universe attracts every other object with a force directly proportional to their masses and inversely proportional to the square of the distance between them. In simple terms, the bigger something is and the closer it is to you, the harder it pulls. Newton's work laid the foundation for modern physics, giving scientists the tools to predict planetary motion and understand the mechanics of the universe. But Newton's theory, while groundbreaking, didn't explain everything. For instance, it didn't clarify how gravity actually works, how this invisible force travels across space. It wasn't until the early 20th century that Albert Einstein offered a new explanation through his theory of general relativity. Einstein proposed that gravity isn't really a force in the traditional sense, but rather a curvature in space and time, or space-time. Massive objects like planets and stars bend the fabric of space-time, and other objects move along these curves. Imagine placing a heavy ball on a stretched rubber sheet. The ball creates a dent, and if you roll a smaller ball nearby, it will spiral toward the heavier one. This is a simple way to picture how gravity works, according to Einstein. This bending of space-time explains why planets orbit the sun. The sun's massive presence warps the space-time around it, and the planets follow paths along these curves. Even light, which has no mass, can be bent by gravity. This fascinating phenomenon was confirmed during a solar eclipse in 1919 when scientists observed starlight curving around the sun. On Earth, gravity gives weight to physical objects and causes things to fall. When you stand on a scale, what you're really measuring is the gravitational pull Earth has on you. The force we feel depends on the mass of Earth and our distance from its center. That's why gravity is weaker at higher altitudes. You're slightly farther from Earth's core. Gravity doesn't just affect planets and stars. In regions of extremely strong gravity, like near a black hole, time moves slower compared to areas of weaker gravity. This concept, known as time dilation, has been confirmed through precise measurements using atomic clocks on airplanes and satellites. Despite all we know, gravity remains full of mysteries. Could there be undiscovered forces at play, or hidden dimensions influencing gravity's strength? The answers might one day reshape our understanding of the universe. Scientists are still trying to understand how it fits with the other fundamental forces of nature, electromagnetism and the strong and weak nuclear forces. Some theories even suggest the existence of gravitons, tiny particles that might carry the force of gravity, though they have never been detected. So, the next time you drop something, remember you're not just witnessing a simple fall. You're observing the pull of Earth's mass, the curvature of space-time, and the echoes of a force that shapes the very structure of the universe. And perhaps one day, we'll unlock even deeper secrets about gravity, the invisible thread holding the cosmos together.
Got a question about how something really works? Drop it in the comments and we might cover your topic in our next video.